Today we discuss important topics related to eigenvalue and eigenvector. Okay, we also start from diagonalization. We write this definition of diagonalization. Okay, so definition of diagonalization, we start from that. A linear operator, we know about that. One operator means one vector space, two vector space. Okay, some function we known about in previous class also. So we'll not discuss about operator now, just a linear operator, and linear means linearity property satisfied on a finite dimensional. Okay, on a finite dimensional vector space. On a finite dimensional vector space, we also know about vector space. Now this one is finite dimensional. Okay, dimension is less than plus infinity. Okay, that means finite number of element in basis. Okay, so it's called what? It's called diagonalizable. That means a linear operator is called diagonalizable. Okay, if there is an order basis, okay, beta for this vector space V such that what? Such that T corresponding to this beta. Okay, that means this operator with respect to this order basis from a diagonal matrix is a diagonal matrix. Okay, then we also call this linear operator diagonalizable. I understand this one, just linear operator is called diagonalizable. Now we also discuss one matrix is called diagonalizable. Okay, we write in this way: a square matrix A square matrix A is called diagonalizable. Okay, if LA operator LAX equal to AX, we know about in previous class also. LA is diagonalizable. Okay, that means LA one operator also. This operator T here LA fixed operator is diagonalizable. Okay, then also that means write this definition of diagonalizable: one operator diagonalizable, one square matrix diagonalizable. Okay, now we're going to discussion about that means how we handle this one. Okay, how we handle this one, also discussion about this topics now. That means a linear operator T. Okay, we erase that portion and going to further discussion of that. Okay, a linear operator T okay, on a finite dimensional vector space, on a finite dimensional vector space V is diagonalizable. Okay, is diagonalizable. Then we also obtain an order basis. Okay, obtain an order basis beta here we represent v1 v2 dot 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 vn, okay, for v. This is for v, such that what, such that this t beta is a diagonal matrix, okay, understood? That means in this way diagonal matrix representation, how this one represent, we write this d equal to t beta, then what happened here, that means for each vector, not in this way, we write here for each vector v belongs to this v, okay, no, vj belongs to this beta, okay, what happened here, that means tvj equal to summation of djj, okay, vi, sorry, dij vi, here I equal to 1 to n, okay, then this one equal to djj vj, okay, then what happened, this one equal to lambda j vj, okay, where lambda j equal to djj, understood? Not a problem at all. So in this way also, that means represent this one, that means each vector t vj equal to summation I equal to 1 to n dj is ij vi, and then this one is obviously, that means diagonal matrix, so djj vj, otherwise all are 0, so djj here represent lambda j, okay, lambda j means we also known about that lambda j means some eigenvalue, okay. So now we also that means going to forward, and that means conversely how we represent this one also, or erase that portion, and that means this one, that means beta equal to this one v1 v2 dot 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 vn basis, okay, order basis is an order basis for v, is an order basis for v, and then what happened, such that what, such that t of vj equal to lambda j vj, okay, lambda j vj for some scalar, okay, then what happened, then clearly what, t beta equal to, okay, t beta equal to in this way lambda 1, okay, 0 dot 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 0 0 lambda 2, okay. So in this way we also written this t beta, okay. I think all I understand this one. Now we're going to that means definition of eigenvector and eigenvalue. Not a problem at all. So we erase that portion and also discussion that portion. Some definition. Okay. Let T be a linear operator. Let T be a linear operator on a vector space V. on a vector space V. A non-zero vector V belongs to this V, okay, is called an eigenvector, of T if there exists a scalar lambda such that TV equal to lambda V. Okay. In this way, also this lambda is what we know about that. The scalar lambda is called the eigenvalue corresponding to the eigenvector V. Okay, this one is representation of eigenvalue and eigenvector definition. Okay, also just easily that means see this one, TV equal to lambda V, then lambda is called eigenvalue corresponding eigenvector V. Okay, T linear operator and a non-zero vector V belongs to V is called eigenvector of T if there exists a scalar satisfies this. Not a problem at all. Now in this way we also that means discussion eigenvector and eigenvalue of some matrix. This one is some linear operator eigenvalue and eigenvector. Now we also discussion that means some matrix. Let A belongs to M n cross n F. That means A be a square matrix n cross n, and obviously which element from this F some field, and obviously some square matrix or are n cross n A. Okay, then what happened here? A non-zero vector V belongs to Fn is called an eigenvector. Okay, is called an eigenvector of A is called an eigenvector of A if V is an eigenvector is an eigenvector of this LA. Okay, then what happened here? We erase that portion and going to further discussion of that. Okay, that means that is AV equal to lambda V for some scalar lambda. Okay, for some scalar lambda, and the scalar lambda is called eigenvalue. The scalar lambda is called eigenvalue of A corresponding to the eigenvector V. corresponding to the eigenvector v. Okay, so in this way we also discuss on this eigenvalue and eigenvector. Okay, now also going to some that means theorem. Okay, we also write this one in a suitable manner in a theorem. Okay, we also write this one in theorem. A linear operator T, a linear operator T on a finite dimensional vector space V is diagonalizable if and only if there exists an Euler basis beta for V, okay, consisting of eigenvector of T, consisting of eigenvector of T. Okay, a linear operator T on a finite dimensional vector space V is diagonalizable if and only if there exists an Euler basis B for V consisting of eigenvector of T. Furthermore, we write in this way. Furthermore, if T is diagonalizable, and beta equal to V1, V2, Vn, Vn. Okay, then what happened here? We erase our portion now. Is an Euler basis is an Euler basis is an Euler basis, okay, of eigenvector of T, of an eigenvector of T, okay, and D equal to T beta, then T is a diagonal matrix. And D is the eigenvalue corresponding to Vj. Corresponding to Vj for 1 less than equal to j less than equal to a. Okay, that means in this way we also that means discussion T diagonalizable beta V, this one is Euler basis of an eigenvector of T, and D representation of diagonal matrix with the T beta, then Djj is eigenvalue corresponding to Vj for 1 less than equal to j less than equal to n. Okay, not a problem at all. So in this way we also discuss on one example also. We erase all this portion and going to some example of that. Okay, we discuss on one example related to that problem. Now we write this one, just example. Okay, a equal to 1 3 4 2, just 2 cross 2 matrix. Okay, here v1 equal to 1 minus 1 and v2 equal to 3 4. Okay, then what happened? Then we also write here, since okay, since LAV1 equal to this one 1 3 4 2, here 1 minus 1 equal to what? Equal to this one 1 minus 2 and the 4 minus 2 2. Okay, then here minus 2 represent 1 minus 1. Okay, that means minus 2 v1. Okay, in this way we also write here v1 is an eigenvector, of LA. Okay, and hence of A, and hence of A. Hence lambda 1 equal to minus 2 is the eigenvalue, okay, corresponding to v1, Okay, next we also discuss in this way. Furthermore, LAV2 equal to 1 4 3 2, here 3 4 equal to what? This one 15, this one 20. Okay, then what happened? Here 5 3 4, here 5 v2. Okay, then in this way we also represent this one. That means the v2 is an eigenvector of LA. Okay, we erase our portion and write this one also. v2 is an eigenvector, okay, eigenvector of LA. Okay, and hence of A, and hence of A. Okay, with the corresponding eigenvalue with the corresponding eigenvalue lambda 2 equal to 5. Okay, not a problem at all. Then what happens is here, that means we also find this LA. Okay, LA equal to what? LA equal to minus 2005. Okay, so in this way we also handle this eigenvalue and eigenvector problem. Okay, I think all are understood this one easily. This one is a easy example. So today I stop here.